Welcome to today's deep dive. Usually when you think about manufacturing metal parts, you sort of expect it to be um, like baking ice cubes. You just melt the metal, pour it into a mold, and boom, you have a gear.
Right, yeah. It is a very comforting thought, honestly. Just a simple, visible, liquid to solid transition.
Exactly. But then you step into the world of precision transmission manufacturing, and that whole ice cube tray analogy just completely falls apart.
Oh, absolutely. It is a totally different landscape.
Yeah, we are looking at a landscape where it is not just about pouring liquid metal, it is about physically forcing the metal's atomic structure to do exactly what you want so it does not catastrophically fail.
Which is incredibly difficult.
Right. It is honestly more like extreme high-stakes baking. And that is exactly what we are decoding for you today. We have got a pretty dense engineering deck on our hands, EP0061 mechanical vocabulary, and our mission is to translate all this heavy terminology to show you exactly how these extreme parts are forged.
And, you know, the best way to really understand this is to look at how engineers escalate their methods based on the stress the part will actually face.
Which makes perfect sense. Start with the basics.
Right, so it starts with just getting the shape right. For intricate components like complex machine housings, the source highlights something called investment casting. People also know it as the lost wax method.
Oh, right. That is where you use wax and ceramic shells to create a highly precise mold.
Exactly. It gives you a near-net shape right out of the gate. Because the mold captures so much detail, you minimize the need to carve away excess metal later.
So you get the complexity you need in one shot.
Exactly.
But, I mean, a housing mostly just sits there. What happens when a part has to actually take a massive beating, say a gear inside a high-speed transmission?
Yeah, casting simply is not going to hold up to that kind of violence. That requires an entirely different approach, which is precision forging. You have to fundamentally alter the metal's internal structure using immense pressure.
And I really love the analogy of woodworking for this.
Woodwork.
Yeah. Wood has a grain. If you chop against that grain, the wood splinters. Metal actually has a grain flow, too, which is just wild to think about.
It is wild, but that grain flow completely dictates durability. When manufacturing things like sun gear blanks, which are the core gears in a planetary system, precision forging forces that metal grain flow to bend.
So they are bending the grain to align perfectly with the shape of the gear teeth.
You got it. You are physically directing the microscopic structure to absorb impacts rather than just shear off under stress.
Okay, so we can align the grain for ultimate strength. But how do you scale that up? I mean, if you need millions of planetary gears, you cannot be custom forging every single one without costs going totally astronomical.
Right. The industry standard for mass producing those parts is actually powder metallurgy, or PM. They take this fine metal powder, press it into a mold, and heat it just below its melting point.
Wait, they just press metal dust together?
Basically, yes.
Yeah.
It provides incredible consistency, and it introduces a fascinating property, which is self-lubrication.
Which is brilliant when you understand the mechanics of it, because pressing dry powder together inherently leaves these microscopic pores inside the metal.
Right.
So engineers can actually vacuum fill those tiny pores with oil, essentially turning the solid gear into a literal sponge. When the gear heats up from friction, it sweats out the oil to lubricate itself.
It is a very clever workaround.
But wait, I have to push back here. If you are literally just pressing dry metal dust together, doesn't that mean the inside of the gear is full of microscopic air gaps?
Yes.
That sounds like a catastrophic weakness if we were talking about like an airplane part.
You hit on the exact limitation of standard powder metallurgy. Microporosity is a massive risk in high-stress aerospace applications. To use those parts safely, they have to undergo a secondary, incredibly violent process.
What kind of process?
It is called hot isostatic pressing, or HIP.
Yeah.
They throw these powder-formed gears into a chamber and hit them with extreme heat and pressure simultaneously.
Wow, from every direction.
From every single direction. It crushes the part inward, collapsing every single micropore. It guarantees absolutely zero internal defects.
So it is like taking that microscopic metal sponge and squeezing it until every single air bubble is permanently crushed out.
Yeah.
You just fuse it into flawless solidity.
That is exactly it. Now let's push the complexity even further. What happens when a part needs absolute solidity, incredibly thin walls, and the ability to bend continuously without snapping?
The deck highlights flow forming for that specific nightmare scenario, right?
Yes. It is used for components called flex spline cups. Flow forming is a rotary extrusion process. By spinning the metal and squeezing it over a mandrel, engineers induce what are known as beneficial residual compressive stresses.
Meaning they are pre-stressing the metal on purpose.
Exactly. They're essentially packing the atoms so tightly at the surface that it artificially increases the metal's fatigue limit.
So the metal is constantly pushing back against itself.
Right, which allows that thin cup to flex millions of times without a microscopic crack ever having the chance to form and spread.
Man, it really shifts your perspective. The next time you are on a flight or using complex machinery, your safety literally depends on these invisible, highly manipulated stresses holding the metal together. It is a precisely balanced masterpiece of physics.
We aren't just pouring metal anymore. We are engineering its atomic behavior to survive conditions it was never meant to endure naturally.
From shaping wax molds to literally crushing microscopic voids out of aerospace alloys. Which leaves you with this to ponder. If we can already manipulate traditional metals at the microscopic level to induce beneficial stress and self-lubrication, what happens when we apply these extreme processes to new synthetic materials?
It is a fascinating question.
Will the precision machines of the future even use metal at all? Something to think about.